If digging ditches is your game, these machines are the biggest and baddest shovels in the pit. From the legendary steam shovel to super shovels with teeth and monster shovels with bigger teeth. The latest scoops are stronger, faster, and even smarter than ever. Now, shovels, dig it on Modern Marvels. Consider the shovel. It may seem uncomplicated, just a blade on a stick. Yet it's actually a precision-designed alloy steel tool that's built to last. They're stamped out by the millions, in dozens of shapes and styles for every possible task. Yet the venerable hand shovel that helped create civilization is limited by the strength of its user. But when human strength is taken out of the equation, the shovel can get bigger, much bigger. Meet the P&H Mining 4100A electric mining shovel. U.S. Borax operates 2 of them. And if moving rock and dirt in a hurry is the game plan, nothing else even comes close. From the ground to the tip of its massive boom, this shovel stands 7 stories tall. Its dipper weighs 85 tons.
We run our 4100s 24 hours a day, 7 days a week, 354 days a year. We typically get 20 hours of operating time out of a shovel each day. He's typically scooping up a little over 80 tons. He can put 3 dippers in a haul truck in just a little over a minute. In 24 hours time, these shovels will load 140,000 tons apiece.
This is California's largest surface mine, operated by U.S. Borax. Borax is a major ingredient in hundreds of industrial and household products. Beginning in 1919, the mine was underground. But today, it's an open pit. And getting to the borax means digging out 50 million tons of overburden per year. That's mining talk for dirt, rock, and other materials covering a precious mineral deposit. At U.S. Borax and hundreds of other coal, copper, gold, and iron mines, quotas must be met, so the speed of the digging is critical. But with a machine this big, the headaches are supersized.
We worry about wear and tear on the shovel. We worry about centering the loads on the truck. That's a big issue. I also worry about my support equipment. I worry about my power cable behind me. Powered the shovel with 7,200 AC volts.
The shovel operator is in a very critical position. There's a lot going on. The bank's changing. There's huge trucks backing in on either side of him or her. The other thing is an operator is under tremendous pressure to produce. These machines make a lot of money and dig a lot of material.
Constant digging and swinging puts tremendous strain on the shovels. That's where the 2.5-inch diameter steel cables come in. This is a wire rope shovel, meaning the high tensile cables do the heavy lifting. The digging starts when a pinion moves the dipper handle and the dipper away from the boom arm and into the digging face. This is called crowding. Then a rope drum, reeling in the hoist cable, rakes the dipper up the side of the face. When the dipper is full, the machine's upper half swings into position, a latch bar releases the dipper door, and the material falls out. A hydraulic snubber or brake keeps the heavy door from slamming shut and damaging the dipper. In any high-capacity mine, these digging cycles are repeated endlessly, an open invitation for human error. They call it boom jacking.
When they're digging with the dipper, they can actually jack the boom up. And if they overcrowd, the boom can lift up slightly, and when it comes back down, tremendous forces are put into the shovel itself. So operators have to continually monitor what they're doing.
You hit a rock, you hit a hard place in the ground, jacks the boom. It shuts the shovel down, locks all brakes. You have to restart it, and it also logs in on the computer that there's been a Stage 1 boom jack.
Advanced software packages are helping operators prevent boomjacking before it causes catastrophic damage. Despite its awesome capacity and $12 million price tag, this shovel bears a striking resemblance to a machine from another age. In 1835, a construction contractor named William Smith Otis built the world's first steam-powered shovel.
It was mounted on railroad rails with small little wheels. It had no house on it. It was just a bare-bone structure with a steam engine. And it had a boom up front and a dipper handle and a dipper that, in its basic crude form, still looks pretty much like the electric mining shovels of today.
But the Otis shovel was ahead of its time, and hand labor was plentiful and cheap. 4 decades later, in the 1870s, rapid industrialization and the expanding railroads heralded the arrival of the steam shovel era. 2 companies emerged from a crowd of competitors to define the shovel for the next century and beyond. The Bucyrus Steam Shovel and Dredge Company and the Marion Steam Shovel Company. Both entered the shovel building race at the same time.
The Barnhart shovel was introduced in Marion, Ohio in 1882, and 1 year later the Marion Steam Shovel Company was formed to build that shovel.
Bucyrus's first steam shovel was called the Thompson, and it was designed to move on rails for an important reason: to build railroads, one scoop at a time. As America's railroads pushed into the frontier, steam shovels were in the vanguard, slicing through mountains and filling in valleys.
The power shovel in those early days was simply mounted on a flatbed car. It was at the end, literally at the end of the railroad.
It would run the railroad tracks up to the hill, and it would actually dig in front of the railroad tracks, and it would turn around and dump off to the side of the tracks into an adjacent track. So as the track advanced, the shovel moved forward and just kind of dug its way through. There were huge crews of people who did nothing but move railroad tracks.
Much like the railroads, surface mining operations used steam shovels to dramatically increase productivity. Between 1880 and 1890, U.S. steel production went from 1.4 million tons to more than 11 million tons.
Without these machines, the U.S. could not have progressed in iron and coal and copper it needed for the growth of industry in the U.S.
The machines rapidly increased in size. Dipper capacities went from half a cubic yard to 6 cubic yards, approximately 9 tons of earth. In 1888, the French gave up on their effort to complete the Panama Canal. 16 years later, American steam shovels went to work on Theodore Roosevelt's grand project.
Panama Canal project was one of the most amazing engineering feats known to mankind. Between the years 1904 and 1914, a total of 77 Bucyrus and 24 Marion power shovels were engaged in moving an incredible 255 million cubic yards of material in that very, very difficult place in the Isthmus of Panama.
In the humid tropics, the work was stifling. Huge work gangs scrambled to lay new track for the shovels to advance, always wary of the landslides that occasionally buried man and machine.
And every week, the progress of each of the shovels were published, sort of a running score sheet of which shovel dug the most. The champion shovel of the week got to fly a broom up there. That meant that was their badge of honor, that they were the best shovel for the week on the Panama Canal.
The new century ushered in many steam shovel innovations. Rails began to disappear, replaced by independent crawler tracks. In 1914, the Ball Engine Company of Erie, Pennsylvania, began producing steam shovels for the small contractor. Renamed the Erie Steam Shovel Company, it built its first model with crawler tracks in 1921, the Erie B. In the farmlands of eastern Pennsylvania, mechanic Ray Fleetwood has restored his very own 1921 Erie B shovel to its original working condition.
Basically, the machine is close to the way it came out of the factory.
It's not totally restored, but I do work on it, you know, mostly on the weekends. There's still some things I want to do to it, but it's a hobby.
The onboard crew of a vintage steam shovel includes 2 workers, the operator and the fireman. The fireman shovels coal at intervals to maintain a hot fire. He also monitors the steam pressure to ensure a constant supply of power. Fire and water are the only elements the Erie Bee needs. Water is periodically injected from a 275-gallon tank into the hot boiler. The water is converted to steam, which creates enormous pressure. A series of valves regulate the pressure as it travels to a main gearbox. The gears transmit power to several pistons that control the dipper's motions. Up front, the operator works a series of crude levers to facilitate the digging.
The lever on the right controls the speed and the function of the main engine. The foot pedal controls the space. It's like the brake. It controls the speed of the bucket being dropped to the ground.
They were small enough and inexpensive enough that a contractor could buy them and make a good living by using that shovel for city work, basements, housing, apartment buildings. Wherever you needed a small shovel that could be handled on a truck, hauled quickly from one site to the other, an Erie shovel met that need.
In the early 1900s, power shovels were characterized by steam power, although with growing availability of other energy sources, power sources like gasoline and diesel and gasoline electric, diesel electric, and even full electric power sources, these shovels became even more powerful and more efficient.
They also got bigger, a lot bigger. A new class of behemoths called stripping shovels took full advantage of electric power in mining operations. As early as 1914, these large strippers featured booms up to 75 feet long. Their purpose wasn't to load trucks, but rather to use their great reach to excavate huge strips of earth in which rich coal seams were buried. As the Bucyrus and Marion companies scrambled to supply large mining companies with bigger machines, a virtual power shovel arms race began, with each company upping the ante in size and dipper capacity. In the 1950s and 60s, these super strippers became some of the largest land-based machines on the planet. In 1965, Marion unveiled the Captain Shovel. Weighing a record-shattering 15,000 tons, it swung a 180 cubic yard dipper that could hoist a 270-ton payload. In April of 2006, the world's last operating super stripper, Bucyrus's Silver Spade, officially retired in Cadiz, Ohio. The super strippers became too costly to operate and too limited in their range. Today, the versatile walking dragline has replaced the strippers. These more nimble giants swing an independent bucket that can dig deeper and cast material much farther than a stripping shovel. In 21st century surface mines, electric mining shovels have a rival: hydraulic excavators. They don't rely on mechanically operated cables. Instead, hydraulic excavators use diesel engines to drive hydraulic pumps, motors, and cylinders that control the digging motions.
They're very good machines. They have high mobility. Hydraulic excavators are usually equipped with diesel power, so they can move from one spot to the other in the mine quite rapidly. They're very versatile.
After a century and a half of digging and countless configurations, the power shovel has earned a place in the pantheon of earth movers. But not every digging job needs extreme muscle machines. Often, a hand shovel will do, just like it has for thousands of years. You won't find these strange-looking tools at the local hardware store. They have very specific functions. But yes, they are shovels.
In 1993, the largest mining shovel ever built, the Captain, was sold for scrap after a 1991 fire caused catastrophic damage.
To most casual users of the hand shovel, what you see is what you get. Not much cause for celebration, let alone dedicating a museum. But in the historic town of Easton, Massachusetts, a shovel museum is exactly what you'll find. The Industrial History Center at Stonehill College is the proud home of the largest collection of shovels in the world. A snapshot of more than 200 years of American industry.
So this is one row of our shovel storage area. We have over 750 shovels in our collection that represent a variety of shapes and types and dates and manufactured brands from the Ames Company.
In the late 18th century, the Ames Company began reinventing and refining an ancient tool. The company succeeded in designing and marketing a large number of not-so-typical takes on the typical shovel. There may be hundreds of shovel types in the museum, but they all rely on the same physics. A shovel is actually three tools in one: a handle or lever, a scoop, and a cutting blade or inclined plane. The blade cuts into the soil by concentrating power at the sharpened edge. The handle provides leverage for prying out the material. When digging, the soil acts as the fulcrum. The longer the handle, the greater the leverage. When lifting the material, a worker's hand becomes the fulcrum. Depending on the density of the material a worker digs, the blade's angle or lift is either increased or decreased to deliver the best position of attack. Good shovel design didn't occur overnight.
The very first digging tools that would have been used in a kind of shovel-like capacity, we can go all the way back to, gosh, over 100,000 years ago, to some really well-preserved examples of wooden digging sticks from cave sites in Africa, when they were sharpened at one end and probably fire-hardened, placed in the fire to harden the tip a bit, and then used for a variety of things, to dig up grubs, to dig up root crops, to do all kinds of stuff.
As human beings discovered agriculture roughly 10,000 years ago, a crude shovel with a separate handle or haft became a hot commodity.
One of the first things that we see is even in those simple digging sticks, we find people putting part of a large mammal bone on the end of it to reinforce that end of a digging stick to make it harder. But in terms of hafted components, we've got everything from shell to bone. The scapula or shoulder blade of a bison is a real common hafted blade for an early agricultural implement. This is a stone blade that would have been hafted to a wooden handle and would have been used to excavate the earth, to shovel the earth. One of the characteristics that's very nice to see is the very high polish or sheen on the working tip of the tool that would have been the result of this coming in contact repeatedly with the soil. And for archaeologists, that's a real nice sign that it's been used to shovel or excavate soils.
As metallurgy progressed more than 5,000 years ago, the first blacksmiths began forging tools that more closely resembled today's shovels and spades. Rome may not have been built in a day, but it was probably built with shovels. Most were made of wood, and some of forged iron. But iron was often scarce and expensive. So for centuries, many common shovels were wooden, with a thin band of forged, sharpened iron at the leading edge. This hybrid wood and iron-rimmed shovel survived even into colonial America. But for working blacksmiths in the colonies, making a shovel was technically illegal.
The typical way a colony worked was it provided raw materials for the mother country. They generally weren't supposed to be making finished goods. So there were English rules imposed on America that we weren't supposed to have ironworks.
In 1774, a Massachusetts blacksmith named Captain John Ames began churning out muskets and illegal hybrid shovels in large numbers. Both implements were likely used to fight the British. When Captain Ames's son, Oliver, took over in 1803, he moved the company to Easton, Massachusetts. He was obsessed with a single tool.
Oliver Ames, who is the focus of our collection, was one of the first in America to focus on large quantity production of iron shovels, all iron shovels, not just wooden shovels with an iron edge.
Ames' legacy as the oldest continuously operating business in America is preserved by the museum at Easton's Stonehill College. Ames shovels took the lead in building America. Beginning in the 1820s, the Erie Canal and other smaller canal projects spiked the demand for his well-made product. Urban construction, road building, agriculture, and even the California gold rush of 1849 kept Ames's factories working overtime. In the 1860s, the expanding railroads required armies of immigrants, all wielding shovels. Rapidly increasing demand allowed the Ames Company to become the 800-pound gorilla of shovel manufacturers.
By the late 19th century, they were the largest shovel maker in the world. And there were consolidation periods in the 1890s, 1910, and then 1920, 1930, in which they purchased and merged with other shovel-making companies and just sort of got bigger and bigger.
Ames pioneered unique and even bizarre shovel designs for countless markets.
This is a potato scoop, and it's designed to let the dirt fall through and keep what you want to keep, which is the potatoes. It's a very beautiful looking shovel. We have this sort of strange two-handled shovel that we don't know a lot about. It looks like this may have been a prototype, maybe to unload a wagon or something like that, where you need some different leverage points. So this is what's called a forking spade. It's some combination of a pitchfork and a shovel, used for rotating crops or turning over soil and things like that. So here's this series of shovels, and most of these are coffee bean scoops. I mean, who thinks that you need special shovels for coffee beans? But it's an interesting design for rotating the beans, or for just sort of using it more like a paddle. So these are some of the larger shovels in our collection. They're about 10 feet long. This shovel with the square blade is a baker's shovel, used for working in a long baking oven. This other shovel is a telegraph spoon. That would be used for digging a telephone pole or telegraph pole hole. So here's a shovel that at first glance you might think is very old. It's a wooden shovel. Why would we be making wooden shovels in modern times? But in fact, this is a World War II snow shovel. Iron and steel in World War II were being used for more important things like tanks. So in a shovel where you could get away with less iron or steel, you took that advantage. So here is sort of a throwback to an ancient design.
But Ames wasn't just making shovels for the home front. Their tools were used in every war ever fought by Americans. After the rifle, a short-handled shovel was a soldier's best friend. In World War II, Ames resorted to espionage to create its famous folding entrenching tool.
The Germans innovated the concept of a folding shovel, and the German shovel was captured and sent back here to Easton for the Ames Company to copy. And this is a 1943 Ames entrenching tool with the design that people are probably more familiar with, that folds. And Ames continues to make and continued to make these shovels and continued to make enhancements and innovations. So this is a Vietnam-era folding entrenching tool, so we can demonstrate here how it would fold up. This one actually has a pick on it as well.
The world's oldest manufacturer of shovels is still supplying the military and civilians with dozens of modern shovel designs. It's now called the Ames True Temper Company. But today, Ames has plenty of competition. One shovel maker uses sharp teeth and 21st century materials to build what it claims is the world's greatest shovel.
The Ames Shovel and Tool Company produced more than 11 million entrenching shovels during World War II.
Forget about shoveling snow or digging ditches. This shovel is built for speed. Every year since 1975, the World Shovel Race Championship has drawn hundreds of blade runners to determine who rides the swiftest scoop. But because an off-the-shelf grain shovel has a limited top speed, the event welcomes fully tricked out, customized shovel sleds, part of the official modified shovel division. The only rule? The vehicle must be built around a shovel blade that contacts the snow. These guys may use science to make shovels faster, but in 1911, a researcher named Frederick Winslow Taylor used science to make shovels more efficient. Taylor published a groundbreaking book, The Principles of Scientific Management. His research involved studying the efficiency of various labor activities in a steel mill. He called one of the studies The Science of Shoveling. Clipboard and stopwatch in hand, Taylor carefully observed workers to determine what could make them more productive and suffer fewer injuries.
If you pick up too much material in your shovel, you get tired really fast. On the other hand, if you pick up too light of load, you're just wasting motions. So Taylor, through his calculations and measurements, concluded that 21 pounds was the optimal weight in which a shovel should carry a load. With 21 pounds, you're not wasting energy, you're not getting tired too fast.
The 21-pound rule and a number of other shoveling recommendations are considered some of the first successful ergonomic studies in history. Taylor's findings prove that matching the correct size and style of shovel is half the work. In the shovel aisle of today's hardware store, Taylor's study has come full circle. Different carbon steel alloys, blade thicknesses, grip styles, and composite or wood handles can make purchasing a shovel seem like more work than actually using one.
The main thing that's changed on shovels over the years has been the method of manufacturing and how they're made. Originally, they were individual tools made by blacksmiths in blacksmith shops. And of course now, they're stamped out very rapidly.
The Seymour Manufacturing Company in Seymour, Indiana, set out to produce the world's greatest shovel.
This is our Structron line of shovels. It's a premium quality, top of the line. We say the world's best tools. This is probably the most common. It's a round point shovel. It's primarily used for digging. The square point shovel is primarily used to move loose material like sand and gravel.
Many of Seymour's shovels are made with high-quality northern ashwood handles. They start as milled 2x2s and then are machine lathed into rounded handles. But for some shovelers, stronger and lighter weight fiberglass is the preferred high-tech upgrade. To achieve its lighter weight, the Structron handle is hollow. The tube is composed of a fiberglass mat, surrounded by millions of fiberglass filaments. The shovel head itself is a heat-treated carbon fiber alloy steel that flexes but resists bending or breaking. A solid fiberglass reinforcing rod extends 12.5 inches from the handle into the shank, offering maximum strength at this critical stress point. It takes nearly 350 pounds of direct bending force to break the shovel.
And we try to balance it out so that we're not sure whether it's going to bend here at the socket or whether it's going to break here at the handle, because it's balanced out so that we try to get the maximum.
One intimidating member of the Structron family adds bite to its business.
This is our exclusive super shovel. It has the teeth on the end. It's extra strong. It's good for digging in hard clay soils or rocky soils. If you hit roots, they won't slide off. They'll chop the root instead of sliding off like a round point shovel might do.
Today's shovel manufacturing involves a cookie-cutter approach. The super shovel starts as a roll of raw steel. A 250-ton punch press stamps out the blanks. A 105-ton first form press smashes the blank into a shovel head. One blow forms the scoop and the step, the bent or rolled edge where the shoveler places a foot. A second press forms the rounded socket that will accept the handle. Each shovel head is heat treated for strength and then painted for corrosion resistance. But the super shovel isn't the only digging tool in the shed.
This is a rice shovel used in rice farming and irrigation work. You'll notice the holes in here. They help break the suction when you're in a wet, muddy environment. This is a steel head general purpose scoop. This is a steel head coal scoop. This is an aluminum head grain scoop, and this is a poly head grain scoop hanging here. This interesting one here with the teeth on the end is a roofing spade, and it has a fulcrum here in the back, so if you are getting your shingles up, you get nails, you can raise them up, raise both the shingles and the nails using that fulcrum. This is a fire shovel. The Forest Service likes these for fighting forest fires because they're small and compact, and they don't need to be carrying a lot of extra weight when they're fighting a forest fire. These are obviously snow shovels. This is, most everybody recognizes this traditional snow shovel where you actually are lifting the snow.
For most shovelers, there's little love for the notorious snow shovel. Effective as it may be, using one is literally a pain in the back. A company called Structured Solutions 2 has reinvented the wheel, or more precisely, the snow shovel. The Wovel assigns most of the back-breaking work to a large wheel. The axle acts as an adjustable fulcrum point, and the user gets a mechanical advantage without the sore back. Whether it's a shovel with a wheel or a super shovel with sharp teeth, today's models have evolved to make the work easier. But if you think these teeth are impressive, just imagine what a whole set of these 200-pound choppers can do.
Each year, tens of thousands of Americans suffer back injuries, rotator cuff tears, wrist strains, and broken bones, all from shoveling snow.
The P&H 4100A electric mining shovel rules the U.S. borax mine in California's Mojave Desert. But its birth out of raw steel and precision design may be the true marvel. With their longtime manufacturing hubs in Milwaukee, Wisconsin, P&H Mining Company and its main rival, the Bucyrus Company, play Dr. Frankenstein to these monster shovels. In the vast fabrication buildings, the shovels begin as complex jigsaw puzzles of high tensile steel.
We start out with raw material, we cut it out, bend it, and burn it into the shapes that can be welded together, or we put it on a machine tool and turn it into a gear or a shaft.
Hundreds of shovel components must be cut to tolerances of thousandths of an inch. A necessity because moving parts must stand up to the rigors of 24-hour-a-day mining. But making tough shovel components also means heat treating. That's heating steel and then rapidly cooling it. Shaping, welding, and machining the pieces of a single electric mining shovel can take 5 months. When the digging begins, all eyes are on the business end of the shovel. It's called the dipper, and while it seems little more than a large metal box, it's loaded with sophistication.
What we've got here is a P&H 4100A shovel with a 58 cubic yard dipper on it. This dipper's got a full lip of mechanically attached ground engaging tools on it. Inside the dipper you have an overlaid clad material. That's the shiny material you see in there. That allows the material to slide out and also protect the dipper from wear. The door itself weighs about 35,000 pounds. So as you're closing this door, there's quite a bit of force generated.
At P&H Manufacturing, building the right type of dipper is an exacting process. It begins with on-site research and model testing. Actual scale models are built and then tested in a simulated miniature mine. Designs determine the right dipper shape and style. Then 21st century engineering and some powerful software take over. Finite element analysis is a mathematical computer model of the proposed dipper's stiffness. Engineers apply simulated loads to predict the stresses that the steel will encounter while shoveling. With a final blueprint for various steel thicknesses, shapes, angles, and pitches, this double XL shovel becomes a reality.
This is the back half of a 40 cubic yard dipper that's going to go to an iron ore mine. There'll be another half just like this that gets welded to this. And as you can see, this is a very thick plate on the side of this dipper. This is the lip on the dipper. This is a very heavy casting. It's made out of manganese steel, which work hardens as it goes through the bank. This is the part of the lip that gets welded onto the dipper.
When the pieces come together, the dipper is a formidable shovel. It has to be, working the no lunch break 24-hour shift. But just like humans, all dippers require regular visits with the dentist.
What we're looking at here is the front edge of the dipper lip. And on the front edge of the dipper lip, you have the mining tooth. This is the primary ground engaging part on the whole system. Below that, you have the adapter, which retains the tooth. The teeth are expendable. We go through a lot of teeth.
At U.S. Borax, teeth wear more slowly because the shovel is excavating a softer shale material. a new set of chompers is inevitable.
They're putting on the new teeth. They're a cast tooth. They weigh about 210 pounds apiece. Over the life of the tooth, they'll probably get about 500,000 tons of material. They're very simple to install.
But one size certainly does not fit all. That's where an outfit like California's Berkeley Forge and Tool Company steps in.
What we're looking at here is a variety of different mining teeth. They range in profile and weights, and that's all dependent on the size of the dipper, the power of the dipper, the muck that it's shoveling. For instance, here you have a very narrow profile, which would probably be used maybe for overburden. Something like this might be used for more of a hard rock application.
Berkeley Forge is a rare supplier of mining teeth because it actually forges them by hammering the steel. Forging produces a super hard tooth. To shape these metal incisors, the raw steel is first heated to 2250 degrees Fahrenheit. One by one, each tooth meets its maker. Berkeley's 10,000-pound steam-powered hammer delivers several well-placed blows to form the tooth's shape. A second hammer forms the back extrusion, where it will mount onto the tooth adapter. The tooth adapters are formed in a 1,500-ton hydraulic press and precision milled for a perfect fit with the teeth. To guarantee the ultimate tooth, technicians perform a magnaflux inspection, using ultraviolet light to search for cracks and tiny imperfections.
The life expectancy on mining teeth is extremely volatile. You can have some mining applications where the muck is pretty easy and you can have a tooth last you for a month to 2 months. You can have some severe applications where they'll maybe go through 1 or 2 teeth in an 8-hour shift. I mean, all depends on the type of terrain that you're digging and the intensity that you're mining with.
When these teeth meet the mine bank, even the biggest rocks don't stand a chance. The mining industry is booming. Manufacturers can barely keep up with the demand for shovels. But even at full capacity, P&H Mining Company is limited to producing 20 to 26 large machines in 1 year. And even when a shovel is complete, the bill of sale specifies some assembly required.
As large as our factory is and as high as our buildings are, it is impossible for us to assemble these shovels here, much less we wouldn't want to anyway. There's no way to ship an entire mining shovel from the factory to the mine.
To get to a location like the bottom of the 700-foot deep borax mine in the Mojave Desert, the shovel pieces are shipped in more than 40 rail cars and semi-trucks, and the puzzle is assembled in place. Over a period of 2 months, some 14 well-equipped specialists erect the nearly 3 million-pound, 7-story tall beast. This shovel will dig for years, but it will never leave the mine. Another shovel is designed to never leave its digging zone millions of miles away, the Red Planet.
A P&H 4100 shovel is capable of digging more than 35 million cubic yards in a single year, a volume more than 10 times that of Egypt's Great Pyramid.
Thousands of years of digging have proven one thing. The shovel is indispensable on planet Earth and beyond. From the first of the unmanned moon missions, shovels have helped uncover the mysteries of our solar system. In April 1967, the Surveyor 3 lander arrived on the moon with a robotic arm and shovel attachment. The scoop tested the depth of the lunar dust to show that manned missions could land safely. Several hand shovels made their lunar debut with the Apollo astronauts to collect moon rocks. In 1976, Viking 1 and Viking 2 landed on Mars, toting robotic shovels. The soil samples they extracted tantalized scientists. Later missions, such as the Odyssey orbiter and the Spirit and Opportunity rovers, confirmed the existence of water on Mars. Now it's up to the Jet Propulsion Laboratory's Phoenix lander and its sophisticated shovel to try to uncover evidence of life on Mars.
What Phoenix is really going to do is to go up to the northern latitudes where we know the water actually still exists, albeit in ice form, and dig into it with our robotic arm. The holy grail, so to speak, is if we would find organics in the measurement, which would really be a sign of life.
But getting that robotic shovel to the surface of Mars is a formidable task. When it hits the Martian atmosphere, the lander will be traveling at nearly 12,000 miles an hour. Atmospheric drag in a parachute will help ensure a safe arrival for the lander and its precious shovel.
This lander is actually going to use pulse thrusters to slow its descent down and land itself on the surface in what we call a soft landing. No more airbags and bouncing for this vehicle.
Once the solar panels are deployed, the Phoenix's robotic arm and shovel can get to work.
This is a full-scale model of the Phoenix lander, and as you can see, the robotic arm is here in the stowed configuration. The arm itself has what we call 4 degrees of freedom, or 4 active joints, and we use those to deploy the arm. As you can see, what we'll do is we'll actually lift it up. One of the degrees of freedom is at the shoulder that lifts it up. We also have an azimuth joint at the shoulder, so we have 2 over here. We have an elbow joint, just like a human arm, at the top, and a degree of freedom at the end for the scoop, for the shovel.
Using a rotary attachment on the head, the shovel will first grind into the hard, icy topsoil. Once past the first layer, the scoop will utilize ripper tines, or sharp blades, to trench the surface. A camera mounted on the robotic arm will help JPL scientists observe and direct the digging. At a distance of 35 million miles, this is one shovel that millions of people will be watching.
It is absolutely the first time we're using such a highly complicated mechanism of this sort on the surface of another planet.
The Phoenix won't be the only robotic shovel in the solar system, far from it. Back on Earth, robotic shovels are saving lives. From up to 2 miles away, the U.S. Air Force's automated ordnance excavator can locate and safely remove unexploded bombs. The operator controls all functions of the excavator via radio frequency. Thousands of miles away, this modified Hitachi excavator is sweeping for landmines. Every year, thousands of people are maimed or killed by anti-personnel landmines. In front of the shovel face, a rotary cutter head churns the earth as it aims to trip the buried mines. The mechanism is designed to resist searing blasts of up to 3,000 degrees Fahrenheit. The shovel itself protects the operator from flying debris. In 2004, these demining shovels detonated approximately 4,000 landmines in Afghanistan and 8,000 in Nicaragua. For centuries, whatever the job, the shovel has adapted to fit the need. Its legacy even inspires a gleam of patriotism.
These products literally built America. I mean, it's sort of a catchphrase, you know, X or Y built America, but here's something that literally did.
Not only America, but the world. Shovels have turned the earth in search of riches and dug the foundations of our societies. Judge their importance by the fact that as ceremonial tools dipped in gold or silver, shovels are the very symbol of human achievement.